Before the second episode of RCE starts, I'd like to thank everyone who listened to the first episode. The turnout was better than expected. I'd like to direct you also to our website, rce-cast.com. On that website, you will find a nomination form. We need you guys to keep nominating projects you'd like to hear from. Also, if you have contact information for any of these projects, please include it in the form. You can also find a list of the current nominations there and who we have scheduled to listen to. Thank you and enjoy the show.
Research Computing and Engineering, episode number 2, with Joshua Anderson and Carolyn Phillips from the Hoomd project. Guys, welcome to Research Computing.
It's good to be here.
Thanks, Brock.
Hoomd stands for Highly Optimized Object-Oriented Molecular Dynamics. And so Josh can give us a real quick of what's unique about Hoomd.
Well, what's really unique about Hoomd is that it runs on NVIDIA graphics cards instead of your normal CPU. Most molecular dynamics packages run on clusters of CPUs, and Hoomd's big advantage is that on just one GPU you can get the performance of about 30 to 40 CPU cores on a cluster.
That's pretty impressive. So one of these GPUs, though, I mean, you can just put one of these things like in a desktop computer in a lab. They tend to draw quite a bit of power, but compared to the number of CPUs you'd have to replace that with, so it's actually quite a nice trade-off, right?
Yeah. The cost savings are pretty good, and it's an especially a good advantage in, say, the research group I'm working in, which is fairly small. We don't have a lot of resources to work from, so running on GPUs right now for simulations, I'm getting a lot more work done than I could have done on the clusters we have access to.
Okay. Some of the other more common MD packages out there are packages such as NAMD, LAMPS, Gromax, and a couple others like DL Poly. What one would you say Hoomd is more closest to? Which one would you say Hoomd is really geared towards working alongside?
The quick answer is LAMPS, and that's because I really like LAMPS a lot. I've been using it for several years, ever since a postdoc from LAMPS introduced a postdoc who was previously at Sandia introduced me to it. So the advantages I really like about LAMPS is that it's extremely configurable. You can set LAMPS up to do probably thousands of different kinds of MD simulations. I don't know. It's just so configurable. It's insane. So Hoomd was modeled entirely based on that same architecture. To be, right now I don't have all those features in, but the architecture is there that any feature to add those kinds of simulations can be added.
Okay. So Hoomd's C++ like LAMPS, or is it something different?
C++.
It's all C++, but you have a Python interface. I notice it actually invokes a Python module.
Well, some of the things I did when developing it is I took a lot of the things about LAMPS that I didn't like and got rid of. And one of the things I didn't like about LAMPS was that they wrote their own kind of parser to parse the scripts. I guess this hasn't been mentioned yet, but all simulation jobs in LAMPS are defined in text scripts, and LAMPS parses them and creates classes based on the script entries you put in. And I didn't want to rewrite a parser myself, so I just use a Python as the parser, and all classes in Hoomd are interfaced to Python objects. So Hoomd script to run a job is actually a Python script.
So actually a user of Hoomd can take advantage of all the power that Python has. So you didn't necessarily have to implement every single option there. They can just use stock stuff from Python, or even include their own Python modules, and then just use Hoomd to actually do the final MD.
Yep, that's a definite possibility.
Okay. So you've actually been doing work with Hoomd using multiple GPUs. How has that been going? How does it scale? And how does it compare to like running on a normal cluster of distributed memory nodes?
Well, it's going back to when I first originally designed Hoomd, when I put it down on paper, I made the decision right then and there that I was going to design it to be as fast as humanly possible on a single GPU and forget about all aspects of scaling. So that was the state of Hoomd for the first, year and a half. It only ran on one GPU. Recently, I've had some motivation to get it running on multiple GPUs, so I went back and sort of hacked in a multiple GPU communication and to split the calculations across. And the amount of communication required on each time step is fairly significant. So it doesn't actually scale very well. Sort of the best scalings I'm getting right now are running on 2 GPUs is about 1.4 times faster than running on 1. Hopefully with a little bit more tweaking I can get that number up. But I'm not very optimistic about scaling past 2 GPUs at this point.
But right now, like you said, the relative performance of one GPU to is how many cores again?
Well, for a concrete example, like one GTX 280 is as fast as around 44 CPU cores on an Opteron cluster.
So this is like trying to take a 44 CPU job and make it run on 88. I mean, this is not a trivial kind of scale to do.
With the clusters, there's the InfiniBand communication, and that's all that communication is distributed over those 44 nodes, and I'm trying to do all that communication all in just one system, and the bandwidth between the GPUs is so slow. I can say that it's around 3 to 4 gigabytes a second is achievable, but that's so slow compared to the 100 gigabytes a second I get on the device that it's hard to work around, at least for molecular dynamics.
Yeah, because I'm actually looking at a run here, which was one of your benchmark cases that I used to burn in a brand new Tesla box. And it was the LJ polymer simulation, I think it was, and I cranked it up to 640,000. It still ran at 24 time steps per second. But the limiting factor here all has to do with how many gigabytes per second it was effectively getting out of the memory of the card. Because the gigaflops reading, you have this nice profile thing. It's really cool. You can just say profile equals true, and it will break down timings and how long things take. The gigaflops is actually very low compared to the peak of the card. But the memory bandwidth is getting up there. So is memory bandwidth more important for this kind of calculation than CPU horsepower? Or in this case, GPU horsepower?
Absolutely, 100%. Memory bandwidth, specifically the device memory bandwidth on the GPU, is what limits Hoomd's performance. And the reason for that is molecular dynamics. It does a lot of calculations, but each calculation on each data element, on each particle, is actually relatively simple. So there's a lot of loading data in, do a few calculations, write the data back out. And so it all comes down to optimizing that memory bandwidth, and that's where a lot of the development and experimentation is done and coming up with the best algorithms for putting molecular dynamics on the GPU.
Yeah, because while the GPU memory is still pretty fast, they do some things differently that's from their graphics heritage, where there's not nearly as much cache, and it'd actually be very difficult to put enough cache on the card.
Yeah, in fact, almost all of the memory accesses are completely uncached, and you have to access them in a very particular way. It's called memory coalescing. There's a certain set of rules you have to follow, and the CUDA programming guide nicely defines all those rules for you, so you know what you have to do.
Okay, yeah. Carolyn and I were talking a little bit before the show about the way this actually works. So when programming on a graphics card, the graphics card really looks like a thread engine. You spawn so many blocks of so many threads, and we're not talking about like 16 or 12 threads. We're talking, 240, 400, 600 threads, right?
Oh, no, thousands. The GPU, going back to specifically the GTX 280 for a concrete number, it's capable of keeping around 40,000 threads in flight at once.
And context switching is effectively free on these cards.
Completely free.
and all the scheduling is done in hardware.
Yep.
So with the way you've designed Hoomd, what is, in the general case, where most of the time spent doing a calculation, what is one thread responsible for?
Let's step back a second here. Hoomd is a very, very modular design, and we haven't really talked much yet about what molecular dynamics is, but it involves calculating forces on each particle and then updating their position following Newton's laws, and then calculating forces and updating position, and you do this over and over and over again iteratively. A typical simulation, I run 20 million time steps or 40 million time steps. And at each one of those steps is a modular step. I was talking about this with the lamps design. I can swap in and out Lennard-Jones forces or a different type of force, or I can swap in and out constant energy integration versus constant temperature integration. So every one of those modules is running separately on the GPU. And within each module, the breakdown is usually one thread per particle. So one thread is assigned just to load one particle in, do the calculations on that one particle, and then write the data back out.
Okay. So what are some of the things you've done to try to improve performance? You said that when you first set out to make Hoomd, you really focused on one card and making it run out fast on one card. So what did you find that you really had to do with the CUDA programming environment to really extract all the performance from the card? We already said memory bandwidth was very important. They have things like texture caches and other bits of special purpose memory. What did you find you had to do?
Yeah, the texture cache is pretty key in Hoomd. So I'll go back and give more of a little bit of story here. A lot of the implementation of Hoomd, the initial, it wasn't originally Hoomd, it was just a code I was writing for a research paper, because this project started off as me writing some code for fun over a summer. And I managed to convince my advisor to buy a graphics card so I could do it. And a lot of the easy calculations that just had coalesced memory were pretty easy to write. I could write them, and in a couple hours, and immediately would have 20 times faster performance for just that one simple operation. When it came down to the more complicated operations, and in MD actually calculating the forces is probably the most complicated step. It took some experimentation and tweaking to get it to run at its best. So specifically, the issue with force calculation is that forces depend upon all the neighboring particles. And the neighboring particles are not necessarily, particles 1, 2, 3, 4, 5, 6 in a nice ordered row, so you can read them coalesced. It's a very random memory access pattern. And so I take advantage of the texture cache for that, and that provided an immediate boost over coalesced memory.
About how much of a boost did just that one change get you?
Oh, let's see. Can I... Well, I wrote the original kernel using just memory accesses just to test it and get it up and running. And then when I changed to textures, it got something like 5 times faster, 6 times faster. I don't remember exactly. In that
That's
ballpark.
That's a pretty significant improvement. There are a lot of people who are pretty happy if they get a 20% improvement from their code.
Yeah. When that's the thing when you're doing these GPUs. If you compared to the CPU, it's 20 or 40 times faster. You're not talking percents there. And then when you start dealing with the memory, if you access the memory in the wrong way, it can easily mean a 5 or 10 times performance. 5 or 10, a factor of 10 performance difference. But then, so I had that all tweaked and running on my little test benchmarks, and it was running great. And then I started doing actual simulations, and I noticed the performance degraded over time. And that was another several-week project, digging in, analyzing what's going on. I eventually discovered what was happening was that my benchmark was too artificial. I was actually putting particles in a nice array so that their neighbors actually were correlated. in the array. And as simulation went on over time, those particles diffused. It's a liquid. So by the end, later in the simulation, particle 1 might have neighbors 10,000, 20,000, and 15,000, very widely spaced in the array. So it just totally blows that cache. And the cache is very tiny, by the way, to start with. So it doesn't take much to empty it. So I actually had to implement a data reordering scheme to reorder everything in memory so that particles near each other in memory are also near each other in space, so that when I'm accessing the memory for calculating the forces, I'm accessing particles all within a small window in the memory, at least on average, and then that brings the performance back up to almost the performance of the canned benchmark.
The reordering, though, so it actually ended up being a pretty cheap operation to do compared to the performance improvement.
Yeah. I actually found there's an interesting paper for molecular dynamics on reordering. They discussed about 5 or 6 different reordering schemes, and some of them were fairly computationally intensive. Others were not, and I actually ended up implementing one that wasn't actually analyzed by that paper. They mentioned it as a possibility, and then said, "No, that's not going to work." And after I benchmarked them all, it turned out that one was the least computationally intensive to implement, and it also gave the best performance. So
the best of both worlds, got everything.
The way it works. So it's the advantage to it is it takes pretty complicated pre-computing steps. So I takes a lot of computation to generate what's called a Hilbert curve through space. And this Hilbert curve has this interesting property that as you move along the curve, points near each other on the curve are actually near each other in three-dimensional space. And so my reordering operation is as simple as putting the particles into boxes and then walking through those boxes in a Hilbert curve. And I can make it really cheap by just pre-computing the curve and reusing it over and over again.
Yeah, I guess one comment I would make about putting these kind of optimizations on the GPUs is that it kind of changes the sweet spot as to where algorithms are optimized, or which algorithm is optimized. One thing that we did is putting a random number generator onto the GPU for Brownian dynamic simulations. And we found that if you could do something more computationally intensive and avoid ever accessing the memory bank by not having to store a state vector for your random number generator, that you could even get a speed up doing that. So just because of the ratio of the number of computations you can do relative to even a very, very fast memory access.
Yeah, that's definitely the case with these GPUs. There's so much, the current GPUs have almost teraflop worth of computing power, or maybe it's over a teraflop. I don't remember the exact number. And only 100 gigabytes a second of memory bandwidth.
Okay, so yeah, these cards are a teraflop, but only in single precision. Is MD okay in single precision? A lot of HPC type applications, they need the double precision, and these cards in double precision are actually kind of poor.
Well, they're 1/8 the performance in double precision. So it depends upon your definition of poor. But as far as MD is considered, all the MD that I'm doing for my research, I definitely don't need double precision. I've verified this. There may be people out there doing MD where they really need the double precision, and I'm just not sure of what types of MD really need it and what types don't. I've talked with some people about this, specifically John Stone, who's working on NAMD and their GPU implementation, and at least his opinion for their type of MD, which is more biology inspired, is that double precision is only really needed in a few places, and so you can do a mixed precision calculation, do what you can get away with in single precision, and only do those steps you really need to in double precision, and you can still get almost all the performance benefit.
Okay, yeah, because like you said, I mean, the performance benefits 8x. So that's actually probably a pretty nice trade-off a lot of times.
Well, actually, my worry with double precision is not so much the loss in floating point operations, because you're still talking over 100 gigaflops of floating point performance in double precision. That's all that Hoomd is running at now, pretty much in single precision. I would be worried about having to load in double the memory. It would cut my performance in half.
Yeah, because every number is going to take twice the number of bits to represent.
Yeah.
Okay, yeah, that is quite a bit different. So, in the future, are you looking at doing any type of distributed memory Hoomd, like mixing in Hoomd with MPI and using multiple machines with multiple graphics cards, or are you looking at getting the 2 GPU on a shared memory machine to a higher performance before you move on to doing something like that?
I don't know where I'm going next. I think if I definitely want to look into getting the 2 GPU performance tweaked up a little faster. But as far as scaling past that on a distributed memory machine, I'm not sure what's going to happen. The NAMD folks have something going there. I've thought about it a little bit, and what I've come up with is that I think I need to think more. Come up with a different way of representing the data. Hoomd's design, like I said, is completely targeted at getting the fastest single GPU performance. So need a new angle to come at the problem from in order to get better scaling.
We need to reevaluate everything when putting
data.
on a
Unfortunately, with the memory bandwidth issues, data structures are key, and the data structures that are optimal for single GPU performance are not necessarily the same that are optimal for distributed computing performance.
Yeah. So right now, Hoomd is C++, using CUDA, which is specific to NVIDIA GPUs. If a standard comes out that would support multiple vendors' GPUs, would you say you would port Hoomd, or are you happy enough with the NVIDIA hardware you would just stick with CUDA?
Well, that's a good question, because OpenCL, maybe you aren't aware, is an open standard.
Yeah, I heard the Coronis group has put their stamp on it, saying that it's ready for consumption.
Yeah, I read the spec, and this is just my opinion, of course, but I read that spec, and I'm very familiar with the CUDA programming guide, and to me it looks like they copied and pasted the CUDA programming guide and changed a few things. So it would be, the upshot of that is that it is very easy for any CUDA developer just to jump right into OpenCL as soon as we get compilers, of course, and start playing with it and start writing kernels. The key difference between OpenCL and CUDA is that on the host side, how you actually set up and call the GPU, tell it to run your kernel, CUDA has a really nice API for that. It's really simple. It makes it's just a slightly more complicated than a function call. I mean, maybe Carolyn can add a little bit to this, since she's learned it more recently than I have, how easy it is to use. But OpenCL is a little different. It takes, I don't know, well, it takes like 150 to 200 lines of code just to set up a single function call on the GPU. It's kind of a pain in the butt. So if there was a definite advantage, I would consider porting Hoomd, but right now, just the ease of use of CUDA is so great that I'm reluctant to move away from it.
Just a comment on the ease of using CUDA. When I started to learn CUDA, I had no prior parallel programming experience. And given the tutorials that they have and the way the language is structured, it's relatively easy to set up. So yes, I agree. What do you think about the fact that there's a fair amount of tuning that one does to try to get optimal performance out of Hoomd on each type of graphics card that's coming out right now? I guess I'd be concerned that these new language standards might make that tuning problem even harder.
I completely agree with you, Carolyn. I have no idea how that's going to work out in OpenCL2, and that's another reason why I'm reluctant to try and port Hoomd over. might blow all the tuning out of the water, and everything will have to be rewritten in some different way to get the best OpenCL performance possible. And even when it comes down to that, even if you can tune your OpenCL kernel for an NVIDIA GPU, and then go try and run it on ATI, who's to say that the tuning is going to be the same on each? So
right now, do you actually have different optimizations floating around for different NVIDIA GPUs inside the Hoomd source code?
I've avoided doing that. There are a few places where I could get maybe 2 or 3% more performance if I did do that, but it's kind of a code nightmare to maintain that, so I've avoided doing it. If I could get 10% performance improvement, I would definitely split the code then, but you got to draw a line somewhere. At some point, it's not worth the hassle.
Sure, I could totally understand trying to maintain. I have a hard enough time on our cluster here that I'm administrator on. We have 22 different MPI libraries, trying to keep track of the different compilers and the different network supports. And this MPI library has this bug and works with this software. And I don't even want to think of when you have to start considering a different hardware you're running on top of too, besides the network. This is a totally different area of needing to be ready for the different types of hardware out there.
Most of the tuning between different hardwares is actually done by, I don't know if just-in-time compilers is the right word for it, but there's a certain amount of compilation that goes on right when you load up the program and CUDA sends it to the card. And so a lot of the tuning is done there. There's always more tuning that you can do. But for the most part, CUDA takes care of it.
What fraction of the Hoomd... So when you first start up Hoomd, a lot's actually done on the CPU, but it doesn't take very long. And then you pretty much shovel everything off to the GPU. And does the CPU almost do nothing?
Yeah, that's a good question to bring up. And that is by far the biggest advantage of Hoomd is that it does, I can't say absolutely everything, but almost absolutely everything on the GPU. There's one small calculation done periodically still on the CPU because I've been too lazy to write it on the GPU. It only uses 4% of the total runtime, so it's not a big deal. One of these days I'll get around to doing it. But except for that one calculation, absolutely everything is on the GPU. And so I can avoid this PCI Express memory transfer. I send the data out to the GPU and just run time steps. You can run for seconds without having to copy data back to the CPU, maybe. And that's a big advantage. And it was pretty exciting when I was developing it, because as I was developing it, I originally put in the architecture there to put any calculation either on the CPU or the GPU. And in an object-oriented way, all the independent calculations don't know what the other calculations are doing. And so they just ask to get the data, and the method, the class that provides the data will copy it from the device to the host if it needs to. And so a lot of the methods originally were just written on the CPU just to get it up and running. So I was doing the force calculation on the CPU at one point, and then I wrote it on the GPU. And as I wrote more and more steps on the GPU, even the most trivial step, I left the most trivial step until last. But when I put that most trivial step onto the GPU, it removed the need to copy data back and forth, and immediately my performance doubled from when it had been. So I was, getting, at the time it was like 15 times faster, and then I put this one trivial step onto the GPU, and all of a sudden now it's 30 times faster. So it was pretty good.
So that's basically saying that data transfer to and from the GPU, avoid it as much as possible and do everything, even if it's a simple little operation. Leave it on the GPU, do it there.
Yeah. Unfortunately, that's one of the most challenging things to do in programming in CUDA, but it's what you need to do to get these really high speed ups versus the CPU.
So the biggest hardware benefit you could get would be increasing the bandwidth from main memory to the GPU memory? Or do you not care about that, really? You're fine putting everything at the GPU?
since I've got everything on the GPU now, I don't really care about the PCI Express bandwidth between the host and device. I'd really like to see the next generation GPU come out with 300 or 400 gigabytes a second of memory bandwidth on the device, because that would make for insanely fast calculations on a single GPU.
Well, at a presentation at RCE02, they actually pointed out how GPUs are in the same problem as the CPUs are, where memory bandwidth is growing linearly. Historically, there could be a jump, but it's been growing linearly, and GPU performance has been vastly outpacing that. But it sounds like in your case, the GPU performance doesn't help you that much. You want the memory performance.
Yeah, that's what I want with Hoomd's current design. There are some ideas floating around on how to get it more calculation bound, but nothing real concrete yet.
Hey, Josh?
Yeah.
Why don't you talk about the size of problem that's going to saturate the Hoomd code on the current, or I should say on the cutting edge GPU cards today? Like, if I was a user interested in doing a molecular dynamics problem, what size problem would be big enough to put on to would it be worth using Hoomd for? And then what size problem would I basically be using Hoomd for all it's worth?
Oh yeah, that's a good question, especially from a user perspective. That's an important thing to know. And unfortunately, I don't actually know the answer for the latest generation GTX 280. I can give you hard numbers for the previous generation cards, like the 8800 GTX or the Tesla C870 series. I've done benchmarks on that, and Hoomd really performance gets decent when you get about 4,000 particles on the GPU, and you have to really get above, say, I don't know, I'm kind of pulling a number out of my head here, I don't know exactly, but I think it was around 8,000 before you really hit optimal performance. And then as you go beyond 8,000, performance just, or not performance, but the running time scales linearly up. So it doesn't matter once you're past 8,000 particles on those GPUs.
So that basically means you need to have 8,000 threads running. Is that just mostly for the memory, the intelligent memory manager of the graphics card to do the most intelligent memory prefetching and stuff?
Yeah, well, what it comes down to is that the memory is very high bandwidth, very high bandwidth, but it's also very high latency. And that's why the GPUs are built. I mentioned this number earlier, to run with 40,000, keep 40,000 threads running on the GPU at once. If you're familiar with the specs, the GTX 280 only has 240 scalar processors. So a lot of those 40,000 threads are just sitting idle. But they need to be sitting idle because they've gone out and requested memory, and now they're waiting for that memory. So they're sitting there idle, waiting for this high latency memory access. But while it's waiting, the processor just puts that thread to the side and keeps running other threads.
So if it has the memory it needs, it runs those threads. The other ones have already put in their memory request. The card can optimize which memory it needs to get, keeps it going, and keeps that whole pipeline full to the best of its ability. It's actually a pretty intelligent piece of the hardware.
Oh yeah, and it's all, you try and ask about the details or read about the details, and you can't get the details anywhere. The most details you get are that the memory manager is some complicated beast that is capable of dynamically scheduling memory from all the different processors on the device and somehow optimizing the use of the 512-bit memory bus and moving data. Who knows how it works, but it does work extremely well.
Right. I mean, the point I've heard a number of NVIDIA reps make is that the GPU is optimized when you have the most number of threads in flight that you can possibly have. And in Hoomd, a particle is a thread, right?
Yes. Now, as GPUs become more and more become capable of processing more and more threads, there are areas in Hoomd where that model could be changed, and it could could potentially break out to be more than one thread per particle in certain circumstances. Right now, there's no performance benefit to that, but as more and more threads can be run at once, there might be.
So what is the maximal size problem that one can effectively run on a GPU?
We're limited by the memory on the GPU. So on
well, the Tesla has 4 gigabytes on card.
Yeah, 4 gigabytes on the Tesla is quite a bit of memory. So I don't actually know how many particles you can put into that amount of memory. What it comes down to is it's actually problem dependent, because the highest memory consumption to data structure in Hoomd is actually the neighbor list, which stores all the neighbors of each particle. And the more dense the system is, the more neighbors each particle has. And so for a dense system wouldn't be able to run as many particles as a not so dense system. So it's hard to put a number on it, but at what I would call reasonable densities, at least from my research background, on 4 gigabytes of memory, you could probably run several million particles, which was more than you would ever want to run on one GPU anyways. If you're running several million particles, you want to have a cluster of several thousand nodes to run on.
You mean because even with the speed up, it's just going to take too long to run an individual time step?
Yeah, I don't have that kind of patience. Maybe some people do. That's fine. But if I have to wait more than 48 hours for a job to run, I just don't run it usually. I run a smaller job or do something else. But there's nothing preventing Hoomd from running on systems that large except for patience.
So Hoomd is available on Google Code?
No, we're on... the official website is actually at aimslab.gov/Hoomd.
Okay.
And the code is hosted at Assembler.
Oh, okay. So if someone wants to start messing around with Hoomd, they can get it from the Hoomd website. And if they want to ask questions about it, there's a mailing list or a website, forum?
Yeah, there's a mailing list and also a link to my email address. I answer questions pretty quickly usually.
Okay.
And all the code is open source, so anyone is free to download and play with it and use it for whatever they want to.
And the only requirements are Boost and CMake. Well, and CUDA.
And CUDA. Well, it does compile without CUDA. That's the real advantage, though, so there's not a big reason to not use CUDA.
Okay, guys. Well, I think we're done for now. Josh, Carolyn, thanks very much for your time.